Okay, so what I want to start talking about today, and we'll start off on the just with some math, and then we'll get back on the computer to start to implement a few things, is um, to talk about string to int and int to string. Okay, so the idea is that I can have the number, say 1, 2, 3, 4, 5, and I could have the ASCII string 1, 2, 3, 4, 5. Okay, and they're not the same thing, right? This would be a, uh, let's say a 32 or 64 bit, doesn't matter, but let's just say 64 bit. This would be, 0x 0000. Um, well, let's say it's that'd be the 32-bit version, and the 64-bit version would just have extra zeros. Okay, but it's actually the number, that thing. Whereas this, in how would this be laid out in memory? Well, what's the ASCII code for the number one? Does anybody have their ASCII table handy, or look it up for me real quick? So for the digit one, the ASCII code is, well, 30 is 0, I seem to remember from talking with somebody. So I think it's 31 hex. No? Yes? Okay. 31. So this would be, okay. Uh, is that correct? Yeah. Hex 31. Okay, good. Um, all right. So, but anyway, it would be stored at ASCII, right? Each character would be a separate byte, and there'd be a null terminator at the end. And yeah, okay. So what I want to kind of talk about is, well, what's the sort of procedure to convert from one to the other, right? Because the two assignments coming down the pipe are to do precisely that. One of them is to go one direction, the other is to go the other direction. Okay. Okay. So, which way do you guys want to start? You want to go number to string or string to number? Number to string. All right. Austin chose. Okay. So if I have the number 1, 2, 3, 4, 5, okay, um, and I want to store a string of the number 1, 2, 3, 4, 5, the thing that goes in just before the null terminator is the number that should be in the ones place. Okay. And then what should go to the place to the left of it? Tens, hundreds, etc. Okay. Good. So how can I figure out the ones place of a number if I've got that number in hex? Or for that matter, the tens place, the hundreds place, and so on. Okay. So how do I know what the ones place is here in the number 1, 2, 3, 4, 5? I mean, we can just look at it and be like, well, it's 5, right? But how do we really know that? Oh, and by the way, here, um, uh, let me actually make one minor change here. If this number is in hex, that's not what I mean. So let me write 0D here to mean that I'm writing this in decimal. Sorry. Okay, hang on one second. Let me make an edit here. Okay, so the number 1, 2, 3, 4, 5 in hex would be 3039. Okay, is that all right? So if we looked in memory, or we accessed that register, in hex we would see 3039, but in base 10 is really 1, 2, 3, 4, 5. Yes? So we have to remember that ultimately the computer has the number encoded in binary, not in base 10. Okay, so we could stare at the digits 1, 2, 3, 4, 5, and you look at that and say, McKinney, I'm not a moron. I know that 5 is the ones place. But if you look at the number 3039 in hex, which is what's actually like in a binary sense there, is it obvious that 5 is the ones place? No, it isn't. Okay, so how do I get the 5 out of this is the question. Yeah. Okay, so if I expand the hex form, so what I think you're suggesting is to do 3 times, this is really 3 times 16 cubed plus 0 times 16 squared plus 3 times 16 plus 9. Is that what you're suggesting? Okay, so good idea, but that's not going to work. And the reason is, what is 16 squared, cubed, 16? Like, do they all have zeros in their ones place when you square them out? No. Okay. So that's not going to work, but something very similar will. Okay. Namely, what does 1, 2, 3, 4, 5 mean? Right? It means that. Okay. So what about if I take a number and I divide it by 10? Okay. So let's say I take a number 1, 2, 3, 4, 5, and I divide it by 10. Then it's going to be equal to a quotient, oops, sorry, times the divisor plus a remainder. Yes? Okay. So, do you guys buy that math? Okay, so another way to say this is that 5 is the result of doing 1, 2, 3, 4, 5 minus 12 times, 1, 2, 3, 4 times 10. Okay, so let's look at what all the pieces are here. This is the number, this is the quotient, and this is the divisor. Okay, so do you guys accept that this is this works out correctly, like mathematically? Yeah. Okay, so when I say the quotient here, like if I divide 1, 2, 3, 4, 5 by 10, okay, what do I get? Like just from a calculator standpoint, what do you get? Yeah, 1, 2, 3, 4.5. Okay, so in this case, the 5 is the remainder. Okay, but when let's think about this from a data standpoint. Okay, the number that we started with, 1, 2, 3, 4, 5. What type of data is that we would store it on the machine? It's a number, yes, but what kind? It's an integer. What number did Artie just tell me? He told me a float. Okay, and you can't just convert back and forth between them. Okay, so what Artie's calculator actually did was you gave it 1, 2, 3, 4, 5, and it interpreted that as a float, not an int. And it did the division, and it returned a floating point answer. Okay, so that's not going to work for our purposes. Okay, because what is 1, 2, 3, 4, 5? It's an int. Okay, so we have to do integer division, not floating point division. Okay, we'll talk about floating point later. Okay, so does that issue make sense? We have to work only with integers here. Okay, so this asks, or maybe begs the question then, how do we do division with our particular processor? And maybe on the same subject, let's go back kind of a ways. What was the trick, or a trick, it was part of the trick with the Caesarean cipher that you guys had to do in order to get things to wrap back around if you hit the end of the alphabet? You had to use the modulus operator, right? The percent thing in C. Okay, and you, in that case, took the modulus upon division by 26 because there were 26 letters in the alphabet. Okay, here we would do essentially the modulus operation, but with 10 as the divisor because we're working with a base 10 number. Yes? Okay, so so I need to know how to do division on the processor. Okay, so let me flop back real quick to the Pi, and let's just do a quick demo of that. Okay, so where's my file structure? And let's make a new folder, and let's call it, let's say, string to, oh, this is IntToString. Okay, and then we'll go over here. Okay, so let me just make a quick demo for the division. Okay. All right, and switch it over to ARM64. All right, so the usual suspects. Okay, so the usual drill there. Okay, in the data section, I'm going to do, let's do the following. Let's make a string, and it'll be this. Okay, or actually, let's say that, let me change it one way. Let me do, okay, let's do this. Okay, and let's use, just for sake of demonstration, our number 1, 2, 3, 4, 5 as our first number. Okay, 10. So when we print this, we'll do 1, 2, 3, 4, 5 divided by 10 gives quotient blah and remainder blah. Okay, make sense? Okay, so let's set up the stuff for the two numbers. Well, the first two numbers are easy. Let me move x0, or actually, for reasons that'll become clear, let me later. Well, I'll do it in W1 instead of X1, whatever. I'll just do 32-bit here. So let's load in 1, 2, 3, 4, 5. Okay, and in W2, let me load just the number 10. W3 and 4 are things that I have yet to compute. Okay, but W3 will get the quotient and W4 will get the remainder. Okay, so in our particular example, what was our quotient that we would expect to see for the number that we're crunching with right now? Huh? I didn't hear you. Sorry, Vinny. Yes. 1, 2, 3, 4 with remainder 5. Okay, so yeah, okay, good point about the 0.5 versus 5. So let's think back to when you guys were in elementary school and you first learned how to do division, right? If they had given you a problem in fourth grade that said, what is 1, 2, 3, 4, 5 divided by 10, you'd go through all the steps, right? And then how would you give the answer? You would have written 1, 2, 3, 4, remainder 5, because 5 is less than 10, so you can't divide 10 into 5. Okay, good? Yeah, we remember that? All right, so then a little later, like in fifth grade or maybe middle school, they said, no, 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 stop with this remainder business. We can keep going, right? And then they told you to keep going with decimals or whatever. Yeah? All right, so now you're in college, and I'm saying, no, 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 don't do what you did in middle school, do what you did in elementary school. Okay, because in some sense, the remainder is actually the important bit, right? Now, how many of you guys have taken Math 108 or, right? So you guys have talked about modulus, right? And modular arithmetic and stuff. Yeah, like hugely important mathematically. Okay. So the quotient will just be the result of the division, okay? And the remainder will be something that we have to kind of calculate in a relatively easy way, but we'll still have to calculate it, okay? So for W3, I want W3 to have the result of dividing 1, 2, 3, 4, 5 by 10. And the way I do that is actually just with the div operation. That's maybe not surprising, like so. Okay, now I want to be clear that this is integer division, not floating point division. Okay, so if I divide 1, 2, 3, 4, 5 by 10, what's going to end up in W3? What do you think? Just 1, 2, 3, 4. Okay, without the remainder. Okay, would we like to have the remainder? Yes. Okay, and in order to do it, we need to do a computation. Okay, so the division operator on ARM architecture only returns the quotient. It does not return the quotient and the remainder. Okay. Now, that's not true on all architecture. So I believe on Intel architecture, if you do a division, it puts the a quotient in one register and the remainder in another register. Okay, which is kind of handy, particularly if what you're interested in is the remainder. Okay, we don't have that luxury, unfortunately. Okay, so what we'll have to do is manually calculate it. And the way that we'll calculate it is like we did on the iPad. I'll do 1, 2, 3, 4, 5, my original number, minus the product of 10 and the divisor. Okay, so in order to do that, I need to multiply 10 and 1, 2, 3, 4. 1, 2, 3, 4 is sitting in W3. So I'll put this result of multiplying there. Okay. So I'm going to compute 10 times my quotient. The quotient was I put in register 3. The thing I'm multiplying by the number 10 was in register 2. Okay, so if I do that, what's in register 4 right now will be 1, 2, 3, 4 times 10. So 1, 2, 3, 4, 0, right? And then I'm just going to subtract and do W4 as the destination, and I'm going to do W1 minus what was in W4 already. So if I do 1, 2, 3, 4, 5 minus 1, 2, 3, 4, what's going to end up in W4 when all said and done there? I would hope it would be 5. Yes? Okay, excellent. So now we have our dividend, the thing we're dividing into, 1, 2, 3, 4, 5 in register 1, the number 10 in register 2, the quotient in register 3, and the remainder in register 4. And now you see why I did 1, 2, 3, 4 for the registers rather than 0, 1, 2, 3. Yes? Because now everything's exactly where it needs to be for printing, and I don't have to move anybody, except for I've got to load the address of the string. Yeah? Okay. So, and then I'll print it. Okay, so question, preguntas, fragen. Let me get rid of some of this white space. Oh, and by the way, I had a sort of epiphany yesterday that I've been a bad professor. Because you know what a good professor would have done is, all these programs that we write in class, the code for them, he would post them. Um, and so I'm going to set up a GitHub repository so I can just like hit a button and then poof off it goes. So coming soon to a Canvas inbox near you. Okay. Um, yeah. Oh, yeah. Good point. Yeah. Well, I'll just do it for all of it. So, I just got to get the repo set up and then push everything. And, so give me a few days. And, well, let's just say that tomorrow, okay, you are all on notice, by the way. Tomorrow at 4:25, I am walking out of my office door and you will not see me again. Well, you might see me. Okay, but work, as far as I'm concerned, ceases tomorrow at 16:25. Okay, at 16:26, I will begin imbibing. Okay, um, huh? What's the occasion? Well, I turned 40 on tomorrow. Actually, technically, no, tomorrow, not Saturday. Yeah. Although technically my birthday is also today. Now, this begs the question, how is it that it's possible to have two birthdays? Okay, any guesses? Yeah, right at midnight, right? I'm halfway in and out. Yeah. No, that no, that's not how it worked. So, uh, but on like a global scale, I was born in Guam. Okay. Huh? Yeah. Yeah. Okay. Do you guys know where Guam is? It's a very tiny island. Huh? Yeah, like almost all the way to Japan. Like it's way the hell out there. Okay. My dad was in the was stationed there, right? He's a Marine. Guam, by the way, is a U.S. territory. Okay, so I can still run for president. Not that I'm going to, but and even if it weren't, I was born at a naval hospital, which is American soil anyway. So yeah, so yeah, I was born on uh, the 11th in Guam, but after the birth, when my parents called my grandparents and stuff to deliver the news, it was the 10th for them here in the States. Okay, so strictly speaking, my birthday is today because it's the 11th in Guam already, or almost, right? So, yeah, anyway. But yes, tomorrow I become an old man. And as such, at 4:26, okay, I'm going to start having a good time. Okay. You may or may not find me at Wally's. Okay. Huh? I'm about to be OX or 0x28. Hey, that's what I ought to do. I just ought to tell everybody my age in hex because I'm not 40, I'm 28 hex. Yeah. Brilliant, Artie. That's why I like having you around. Okay. Yeah. Anyway. Okay. So that's going to do all the computations and we're ready to go. Yes? Good? Okay, so let's assemble this and run it and make sure everything works correctly. Let's get a terminal open. Oh, for our final? Oh, yeah. It sucks to suck, by the way. Okay, what did we call this? It was int to string, and we called this div demo. All right, so as div demo dot asm output to div demo dot o. Oh, right. Crap. It's not div. What is it? One moment, please. There is an operation. I'm just blanking on it. Oh, yeah. Okay. Sorry. Um, it's um, it's not s. It's not div. It's udiv. Well, either udiv or sdiv. Okay. So the difference is signed versus unsigned. Okay. And in this case, I'm going to go ahead and do it. Well, let me just do udiv for right now. Okay. Um, and let's make sure that that works. Yeah, there we go. Okay, good. Um, all right, so it's not just div, it's either udiv or sdiv, okay? And the difference is whether or not it's signed or unsigned, okay? Um, should we be able to handle correctly the case of negatives? Hopefully, okay? So there's two ways to think about dealing with a negative. Well, let me change this to signed div, and let me make my number here negative 1, 2, 3, 4, 5. Okay. And is that correct? Sort of. Okay. But what does remainder minus 5 mean? Yeah. Okay. So here's my suggestion. If the number is negative, can you detect that fact from the get-go of the program? Yeah. Like you can look at a number and with a branch or a comparison, know very quickly if it's a negative. Okay. So I think the easiest way to handle this would be if the number is negative, flip it positive and process it accordingly, and then deal with the minus sign later. Does that make sense? Okay. So, so we've got that. Okay. So that's how we can extract the digit 5. Now, if I wanted to extract the digit 4 as being the tens place, what would I do? Okay. Two options. Julius just said divide by 100. What's the other option? Yeah, loop this. Okay, because then I could take 1, 2, 3, 4 and put it in register 1. And if I divide it by 10 and do the same thing, what am I going to get? 1, 2, 3, remainder 4. Okay, and so I can just loop this procedure, right? And that's actually the way that you want to go about it. Okay. Multiplying by larger, like dividing by 100 and then dividing by 1,000 and stuff, that would also work. But I think what's going to be more elegant and actually the way you need to go anyway is what um, uh, Jaden suggested. Huh? Well, yeah, I know, right? Senior moment, okay. I guess I can't make senior moment jokes until Monday, right? Okay, so and the reason that the looping approach is going to be better is because you got to get all those digits out anyway. So you're going to have to loop anyway. So you might as well just do that. Okay. All right. Now, what's going to be the next step in terms of taking this number 5 and producing a digit 5? Okay, so once we have the number 5, we ended up putting it, I think, in W4, but it's in some register, okay? I need to take the number 5 and convert it into the ASCII value for the digit 5. Well, what's the ASCII value of the digit 0? 30. Okay, so what's the ASCII value of the digit 1? 31, 32, and so on. Okay, so this value of 30 hex is my base value. And if I add 5 to 30 hex, oh, that's the worst looking 5 ever. Okay, so if I take 30 hex and I add my remainder to it, which in this case was 5, I get 35. And guess what that's the ASCII code for? The digit 5. Okay, so now I have the actual ASCII thing. I have a character for the digit 5. Yes? I should store that someplace. Store it and loop. Here's the one problem, though, with storing it. Where am I going to store it? Stack, maybe allocate some space in memory. Okay, so I'll store it someplace. And let's say that here, let me draw out a segment of memory. So let's say I allocate some segment of memory and I go through this processing, and then I'm going to be like, okay, so 3.5 goes here, and 3.4 would go there, and 3.3 would go here, 3.2, 3.1, and finally null terminator. What's the problem with that string that I've just produced? It's backwards, right? Because which digit did I figure out first? The 5, which should go on the far right. But because I figured out first, if I start storing this stuff into memory, I'm actually going to put it on the far left. Yeah, those are all hex values, not decimal, sorry. Okay. So my string is in the wrong order. It's completely backwards. Yes? Okay. So do you think what might be a useful function to write then? How about a reverse function? Yeah. Okay. So given a string, can you reverse the string? That's going to be really handy. Guess what you get to write? A reverse function. Okay. Now, here's why we have to do a reverse function. Or, okay, you don't have to, in the sense that if you go back to the drawing board and think about this, you might be able to get away without having to have a reverse function. Okay. But when I get a number, say 1, 2, 3, 4, 5, do I know in advance how many digits it has? I mean, we do as humans, we can just look at it, right? But from the computer standpoint, if I typed in 1, 2, 3, 4, 5, what it has in memory is hex, what was it, 3039 or whatever it was? Okay, so it has that number in memory, right? Can you look at that and know that you're going to need 5 digits as opposed to 6 or 4 or whatever? No. Okay. Um, And so, as such, it's easier to start processing by figuring out the ones place and then continuing. All right, now this begs the question, how do you know when you get to stop looping, by the way? How do you know that? So, if I take 1, 2, 3, 4, 5 and I divide it by 10, I get 1, 2, 3, 4, remainder 5. Okay, I divide again. 1, 2, 3, 4 divided by 10 is 1, 2, 3, remainder 4. Continue. 1, 2, 3 divided by 10 is 1, 2, remainder 3. Continue. 12 divided by 10 is 1, remainder 2. Okay, so when do I stop? When my quotient is equal to 0, exactly. Because then I would do 1 divided by 10, and I would get quotient 0, remainder 1. Yeah? Okay, so when your quotient hits 0, that tells you that you can stop. But do you know how many steps it's going to take until you get there a priori? Okay, so from the beginning, in advance. You do not, right? Okay, because the other part of this program is, for our quick little demo of the division, what did I do to load in the number 1, 2, 3, 4, 5? I just chose that in advance. What are you guys going to do? Accept input from the user using scanf. Okay, so as such, the user could type whatever number. Okay, and I think I specified, just to keep this from having weird overflow issues, to accept no more than 18 digits. I think that's correct. I specified in the assignment, okay, in order to keep the numbers so that you won't have weird overflow or something happening, okay? But you don't necessarily know, like if you accept a maximum of 18, do you know that the user is going to give you 5 or all 18? You don't, okay? All right, so what are the two problems then that, well, three problems you got to crack? How to loop this, but also this produces the string in the wrong order, okay? Can you reverse the string's order? Yes. Okay, what's the other annoying thing that we have sort of swept under the rug so far? Huh? No, not floating point. Yeah, 100% integer. Okay, we'll deal with floats later. Well, what about if the number's negative? What should I have in my string? I should have a minus sign, which is whatever it is in ASCII. Okay, so if the number's negative, it ought to correctly have the minus sign where it belongs. Yes? Okay. Good. So if this is the process to go from an integer to a string, then the procedure to go from a string to an integer is going to be a lot of this, but in reverse. Okay? Because if I get, so let me flip over to a new page. If I have a string in memory, and somebody look up real quick what the ASCII value for the minus sign is. $2D as in delta? Yes, okay. Okay, so if I accept a string from the user this time, and the user types minus 1, 2, 3, 4, 5 as a string, okay, then this is what it would look like in memory, right? Minus sign, digit 1, 2, 3, 4, 5, null terminator. Okay, it's a string. Good? Okay, so I need to know, how do I turn this thing back into a number? Okay, well, I'd start at the right in this case, and how do you know where the right-hand end is? Could you just go all the way to the null terminator and then pop one spot to the left? Okay, so if I have the ASCII value 3.5, what digit does that correspond to? A 5, and how can I get from 3.5 to 5? Subtract the constant 30 hex, right? Okay, and so if I take this byte, subtract 30 hex, I now have the number 5. Can I then process with that? Yes. Okay. If I move on to this one, I have, so I'd get 5, and then I would need to have a running total of 5 plus 3, 4 converts to what? 4, but which position is he in? the tens place, so I do 10 times 4, add that to my running total, and then what? 100, 3 with 100, so I do 3 times 100, add that to my running total, and so on, okay? And then how do you know that you get to stop with that loop? Well, one of two things. Would it be nice to know the length of the string? Yes. Have we written a function that computes the length of the string? We have, okay? The only wrinkle, of course, is going to be the minus sign, okay? Right, okay? Now, maybe one other thing. So if you know the length of the string, you know when to stop so that you don't go too far to the left, if you will, okay? Okay, so notice that the math that we just did was essentially the reverse of the math that we did in the other case, right? I mean, this makes sense, right? These ought to be invertible processes, okay? And then you just build up the number, and eventually you'll, after looping, you get it. Okay, so there's basically all the math that's necessary here. The other problem we need to worry about, though, is what happens if the user types garbage? Okay, so if I ask the user to type a string and they type Wabash, is that a valid string? Not for this purpose, right? It's a valid string for many things, but it's not a valid string for our program here because it's not a string of just the digit characters, possibly with the minus or the plus symbol, okay? So it's not valid for our purposes. So what would be a good idea to do? If you get a string from the user, before you do anything about all this arithmetic nonsense, what would be a good idea? Make sure it's a valid string first before you do anything. And if it isn't, reprompt the user. Okay, possibly saying, hey, dude, bro, you're a moron, right? Okay, so let's talk about the reprompting, like how you could set something like that up as painlessly as possible. Okay, so so let me go back here, and let me do a new function. Okay, and let me do, this will be, all right, so data, text, global main, STP, the usual suspects. Oops, that is not the button I wanted to hit. Okay, so for sake of demonstration, let me make a couple of strings here. Oh, and I'm not going to put a colon in because of what Patrick has told us. Yeah. Okay. All right. So I put here %18s. That will limit our string to be 18 characters. Okay. The other thing I'm going to do is um, um, I'm going to pre-allocate. If I have an 18 character string, how many bytes do I need to allocate in memory? 19 to include the null terminator. So what I'll do is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 zeros, followed by a \0, which is a null terminator. Okay, so that will pre-allocate for me some space in memory where I'll put this string for further processing. Okay, and by pre-allocating, I just put zeros there. It doesn't matter. I just need something. Okay. Um, Okay, so I've got that, and then I might need to have something like your string is invalid, okay, and to reprompt the user with, okay, seem reasonable? All right, so in my main function, let's do the following. Well, we need to set up a call to scanf, okay? So I need to load x zeros with the address of the format string, which is string2. I need to load x1 with where I want this to go in memory, which was the address of the input string. That's the space I pre-allocated for this. Okay, good. All right, and then eventually, um, I want to do some printing and stuff. But for now, I would just branch to scanf. Right? Okay, so good. And so if I run this, well, let's do that real quick. Oh, typo. Oop, didn't get the S when I copied it. Okay, my bad. Okay, so it's sitting there waiting for me to type something. Okay, now it put it into memory where I said to, but we didn't print it or do anything like that, so we don't get any output. Okay, all right, so other than it complaining about not ending on a blank line, are we cool? Yeah, okay, so we've got our input handling set up. Okay, and now what I want to do is decide or have a function that's going to process this string and either accept or reject it. Okay, so for the moment, what I'll do is I'm just going to hard code it. Okay, and the way I want to think about this function is I want to think about this as being something like bool something like that. Okay, so let me actually put this on a new line too. Okay, so if I were to write this in C, then I would be doing something like bool test string of, and then I would pass to it a string's address for processing. Okay, and this thing would return a Boolean, which is, what is a Boolean again in C? It's either a true or false quantity. Numerically, though, this is essentially the same as using an integer, but where it's either 0 or 1 only, numerically. Okay, so I could also do int test string of string and just return the number 0 or the number 1. Okay, in fact, in the assembly, that's exactly how I'm going to do it. I'm going to return either a 0 or a 1. Okay, good? Okay, so for right this moment, let me just um, let me just make my function the stupidest tester in the world, okay? And what makes it stupid is let me just always return true, no matter what the string is that I give. Now, clearly, I don't want that eventually, but just to get the testing working and the rest of the logic, let's just start with that, okay? So all strings are valid for this function. In a minute, I'll change this to a 0, and so it will say all strings are invalid. It will always reprompt. We'll end up in an endless loop, but that way we can make sure that our reprompting works correctly. Is that okay? Okay, so I need to take the test string, okay, or the string that I want to process, and I need to pass this to the function test string. Okay, so how do I pass a string to a function? Well, yes, I need to branch to it, but how do I pass the string part? Huh? I've got to hand the pointer, the address, to this function. So I need to load x0 with the address of the string that I wish for it to examine to see if it's valid. And then I need to branch to, what did I call it, test string? Yeah? Okay, so this sets up the function call. Okay, so test string, yes, go ahead. Because I want test string to be a function. And so I want to think of it as being completely external to the main function. Okay, so I'm thinking of it as genuinely as a function here. So the one maybe hint I'll give, or not hint, but suggestion is if you're going to a function over here, always branch and link to it. That means that that function better have the store pair, load pair, ret stuff. Only ever branch without linking within the function that you're in, okay? If you start mixing the two, you're going to end up with the most crazy spaghetti code ever. It's going to be like if you had a giant pot and you dumped in linguine and penne and bow tie pasta all in the same pot, which probably is what Sparks will serve for lunch today. But you know, when have you guys ever had the when they have pasta and they give you a scoop of pasta or whatever and put sauce on it and it's like multiple different kinds of pasta in the yeah, like they run out of spaghetti so they cook a bunch of penne and then you've got penne spaghetti. Yeah, so yeah, oh Sparks, but they've come very close a few days of running out of chicken tenders on Wednesdays. And we go through an obscene quantity of chicken tenders. Like, there's probably truckloads of, how many chickens had to die for you guys to have Chicken Tender Wednesday? Anyway, okay, so this function is going to return the number 0 or the number 1. Yes? So if let me put a label here called all good. And in fact, let me tab some of this stuff over. Okay, so if the function returns 1, then that means the string is valid and everything's good. So we can go on to the remainder of our program. Okay, otherwise, what do we need to do? We need to reprompt, okay? So I could do this. And just reprompt. Okay, and actually, if you guys will humor me for a moment, Do you mind if I actually put prompt user here? It should go there because, well, it has to go there. It's got to go. Oh, the other thing I should do, right? Did I ever tell the user to type something? No. Okay, so let's do that real quick. What was the please type? So it's string 1. Okay, so that part, these two lines will just print the please type something, and then scanf will do its thing. Okay, all right, so we're good there? All right, so let's test it. Oh, sorry. Forgot to put the register to check. Oh, that's interesting. Hmm. Oh, I never returned. Yep. Okay. I forgot the ret in the function. Okay, great. So this function always returned that my string was valid, and so it would never actually reprompt me. Okay, so the reason I've structured it this way, and I'm going to really emphasize that you guys structure it similarly, is like you guys are really bad at trying to do everything in the main routine, right? Don't write subroutines that handle the individual pieces and have main be how you put them together. Okay, yes, because if you don't, you're going to end up with a complete nightmare of scenario, and you're going to come to my office. You're going to have this giant pile of code. It's going to be incomprehensible, and you know what I'm going to say? Start over. Okay. Sometimes the very best thing to do is start over and just think and not be a moron. Like think structurally before you start typing shit. Okay. Yes. Okay, so let's get the reprompting part tested. Right now, it never will reprompt because I forgot my testing function returning a 1. So let's change this to return a 0, which would mean that my function rejects all strings. Okay, not very useful except for testing the program. So let's run that and see what happens. Seems good? Okay, so that's going to go in an endless loop. But there's one other little thing that we might have to worry about. What did we run into when we did things in C and we were accepting user input? The flush function, right? Sometimes we needed to do a flush. Okay, so let's get that in here. Yeah? Now, did we, in this particular instance of running it, did we actually need the flush? Looks like no. Okay, looked like it accepted and worked properly. Okay, but sometimes you still need the flush function. So even though we got lucky here and it wasn't absolutely critical, let's go ahead and get it in just to cover our butts. Okay, so where is the flush code? It will be in the GitHub repository, but for the moment it's just on Canvas. And I think I put it in an announcement, but it's probably somewhere else too. Here we go. Okay, so I'm going to take that. I'm going to make a new file for it. So I've got my flush function here, and then, and it's not tabbed and spaced and stuff, but that's okay. So I've got it. Why is it giving me a? It just clears the input buffer, right? And I think we technically need to do that so it'll stop yelling about the EOF. Okay, so now I'm going to have to change how I assemble it, because now when I do the, oh, sorry, I forgot one thing. Where should we flush? We should probably flush immediately after, well, there's one of two places we could put it. Either after we get the user's input, so after the scanf call, which would be right here. Yeah, let's put it there. Okay, so I'm going to BL to flush. Yes? Now, flush is written in C, not assembly. Okay, so when I go down here to put all this together, I need to add flush.c to the GCC part of it. Okay, and we don't notice any difference in functionality here, but we've covered our butts. So the flush function is now integrated in to our function here. Okay, and right now, because I have the string tester rejecting everything, it will just be in an endless loop forever. Okay, all right, does that kind of make sense? So this, by the way, and I think I've mentioned this probably a month ago, when we first started assembly, is you can actually mix C and assembly. Okay, and so if there's, and this can be really useful for while you're getting things working, because for example, I mean, Artie mentioned earlier, is there a reverse function in Python? A string reverse function. Yeah. Is there a reverse function, a string reverse function in C? Probably. Okay. But is there, for example, a string length function in C? Yeah. Okay. So let's suppose that you are working on something and you need to know the string length, but right this moment, you don't want to write the string length function yourself in assembly. While you're developing this, just use the C function, okay? And then go back and say, okay, now I need to replace the string length function from C with the one that I'm going to write myself. Okay, does that make sense? Okay, so the following rule. With the exception of the flush function or anything else that I specifically authorize, all of your code must be 100% assembly that you've written. Okay, so if while you're developing and working on something, you cheat for the moment using a C function just so that you can concentrate on one thing, great, right? Don't try and do everything at once. But eventually, when all is said and done, what should you be handing me? Just assembly and say the flush function. Okay. And I will ask you, by the way, that if you use the flush function in any program, you include flush.c in your the files that you submit to me, because that way, if I need to reassemble and recompile your stuff, I've already got the file right there ready to go. Okay, does that make sense? Okay, so then maybe one other thing is, from a user standpoint, would it be nice to tell the user that their string was invalid before reprompting them so that they're not thinking that your program's broken? Yeah. So we made a string and it was called your string 3 that just says your string is invalid and then reprompts. So let's just add in right here, let's okay, just to tell the user that their string is invalid before actually reprompting them. Okay, and then I'll just continue in the endless loop at that point. Okay, good. All right, so let's recap what we've done today, which is sort of three things. Okay, we've talked about basically the math and the logic of how we'll start to piece together taking an int and converting it into a string or vice versa. Okay. Similarly, we also said that in the case of the string to int, it's possible that the user is a bonehead and types Wabash when you ask them for a string that's just numbers, possibly with a minus or a plus symbol at the beginning. Okay, so what would be an example of an invalid string for string to int? Wabash would be an invalid string. 1, 2 plus 3 would be an invalid string. Plus 1, 2, 3 is valid. Minus 1, 2, 3 is valid. Okay, so a minus or a plus symbol can appear, but if they do, where must they appear? Only the first character, right? All other characters must be what? The digits, right? So 0 through 9. And if anything else besides any of those appear, what does that tell you about your string? It's invalid, and so you should reprompt. Okay, so think of the structure of then, like I've given you kind of a shell for how to start some of this. The reprompt part, right? So I had the label there called all good. Okay, that would be, well, now that you know the string is valid, then what are you going to do with it? Okay, so that's when you would call all your stuff to like start processing the string and then outputting the answers and yada yada. Okay, so right. Okay, so don't do too much at once here. Is that okay? Okay, so where do I want to go on, say, Tuesday? We talked here about the division operator, okay, or opcode function. So there were really two, right? Unsigned and signed, okay? For the purposes of the IntToString, I'd actually use the unsigned and at the very beginning check your program and just see, hey, is the number negative? If it is, make it positive, process accordingly, and then stick the minus sign on at the end, okay? That will probably make the math and stuff a little easier to think about, okay? So maybe for the purposes of getting going, just assume the number's positive. Get that working, and then worry about the minus sign, okay? So floating point, right? We would like to be able to do division and stuff and not only be working with integers. And so what we'll have to do is there's a completely other side of the processor that handles the floating point stuff with a complete pile of its own registers. Okay, so the X and the W registers are all integer registers in some sense. There's a complete other pile of 32 more floating point registers, okay, that we can work with. And those floating point registers, the reason that they're separate, well, two reasons, is, think architecturally, okay, or if we think back to like the 1980s, right? In the 1980s, CPUs did not have floating point units on board. They had integer units, were perfectly capable of doing integer arithmetic, but they did not have floating point units. So, how did you do floating point computations back in the 80s? There were two ways. Well, three ways, okay? You didn't, or you emulated it in software, right? So you wrote software that did floating point processing by a technique that we call bit banging, right? Now, as you can imagine, it's slow, very slow, because you're having to basically program all of what a hardware floating point unit would do. Very slow. But, if all you're doing is so for example, if I did a 1, 2, 3, 4, 5 divided by 10 on my Commodore, we'd get the answer basically instantaneously. Okay. But am I doing solving differential equations on my Commodore? No. Okay. So for just quick calculation, just like a couple numbers here and there, it's still fast enough to be usable. But if you're trying to do scientific computing, is way too slow to be practical. Okay. So Intel and other companies, in fact, this is how AMD kind of got its start. Intel sold, in addition to the 8086 or 8088 processor, they also sold a floating point chip that was sort of an add-on chip that would be a coprocessor that would work with the main processor, and the coprocessor would do the floating point stuff. So the main processor would send the data to the coprocessor would do it and send the answer back. And the coprocessor was designed specifically to just do floating point computations. That's it. But it was a separate chip. Okay. These were actually pretty expensive back in the day. And so this sprung up, and they could be kind of slow. I mean, way faster than software, but still kind of slow. So AMD and several other companies, for example, got their start by saying, okay, we know what the instructions are that the Intel CPU will send to the coprocessor, and we know that the coprocessor should send the answer back. So what about if we could come up with our own floating point thing that we could sell and take away from Intel's business of selling its own floating point coprocessor? If we can do a better job and undercut them on price, then who are customers going to go to? Us, right? Okay, so yeah, this used to be coprocessors. Then, starting with, I think it was the Pentium chip, okay, in the early 90s, the first Pentium chips finally brought the floating point unit on board to the processor. So there was no more coprocessor. But it's still inside the processor is as if it's like an embedded coprocessor in some sense. Okay. And that's sort of true in ARM also. There's this floating point unit, which it calls Neon, stands for something. Okay. And it's got its own pile of registers. It's got another set of instructions. For the most part, most of the instructions that we use for working with integer registers work with the floating point registers if you put an F in front for float, right? So for example, if I want to move a number into a register, I use move. If I want to move floating point, I use fmove. Well, that makes sense. Okay. Okay. So we'll start to look at how do we actually use those instructions and registers, but then also, and this is the other key thing. You guys know how I gave you the assignment to do on paper with the for the integer arithmetic stuff, which half of you still haven't given me. Okay. Glare. Okay. There's going to be a similar one for floating point. Okay. And so Tuesday we'll talk about how floating point data is actually stored and how it works so that you can do the paper assignment. Thank you for taking off the frillies, Patrick. Okay. By the way, the following rules now apply. If you turn in an assignment with frillies on it, I'm going to burn it. Okay. All right. So I'll see you later.